Okay, so in the little writing thing that I just did, a lot of people said they wanted to know how chemistry and quantum mechanics even connect to each other. Quantum mechanics, the reason we're having you take this class, and the reason that this is important, besides the fact that I love this is what I spent my PhD on, and is what made me stick being a chemistry major. All of chemistry, when we're talking about reactions, reactivity, how things happen, it's all from how the electrons behave. And quantum mechanics really gets to how the electrons behave. When we first learn about reactivity, even organic chemistry, the biochemistry, we're really just learning based on patterns. We're kind of observing what's happening, and we're saying, hey, this is a kind of common pattern we see, and we can predict other things. It turns out the development of quantum mechanics, and the use of quantum mechanics, particularly in chemistry, has kind of revolutionized biology, biochemistry, genetics, polymers and coatings, anything where you've got an electron cloud that you need to understand, and maybe understand even before you make the material. Quantum mechanics gives us the ability to do that. Most of you at this point, since you're all seniors, have probably seen electrostatic potential maps, where you see like the cloudy bit around a molecule, and the cloudy bit is where the electrons are likely to be. That's calculated from quantum mechanics. That's determined from knowing how electrons behave, being able to write down equations for how electrons behave, and then clumping hundreds of electrons together to see how they behave as a bulk material. And so we're going to kind of get into that in a slow way, starting with very simple ideas. And by the end of the quarter, we're going to build up to the idea of molecular structures and the electron cloud around a molecular structure. But I want to start with just doing a little bit of physics review. Because when I took quantum mechanics, and if you read the textbook, the first assigned reading, quantum mechanics just drops out of the sky. It's just like, ta-da, there's quantum mechanics, black body radiation, photoelectric effect, atomic emission spectroscopy, and low temperature heat capacity, ta-da, now there's quantum mechanics. And that bothered me. When I was a student, I was like, it just comes, first off, I was just blown away that people could just make this up out of nowhere. It's not made up out of nowhere. All of quantum mechanics actually begins with some classical mechanics applied to strange systems that don't exactly line up. And this leads to two important ideas. The first idea is the correspondence principle. The correspondence principle essentially says, I'll give you the exact language. Well, let me give you the exact language first. The exact language of the correspondence principle is, quantum theory must asymptotically approach classical results for a large set of quantum objects. What does that mean? Classical mechanics, that is to say Newtonian physics, your general physics, like a ball rolls down a ramp, all that stuff works. All that stuff still needs to work once we take quantum theory and we build it up. So most of what we talk about with quantum theory is atomic scale, 1 or 2 atoms, maybe 10 or 20 atoms. Correspondence principle says, as you build that up to a larger and larger thing, to the point where you've got a water bottle or a desk, it better just behave like a desk. So the correspondence principle essentially says, so when we talk about the quantum level versus the classical level, quantum level is really looking at that's when you're looking at 1 to 100 atoms interacting with each other. So we've got some collection of atoms. 100 gets pretty difficult. We probably won't get far past 8 or 9 atoms behaving together. After you get to like 4 atoms, it's computer simulations, because you're dealing with large equations at that point. But quantum does okay on the 1 to 100 atom scale. The classical level, that is to say, what everyone did in the past before quantum mechanics, that's like 10,000. It's like 10,000 atoms and above. Like when you've got 10,000 atoms kind of working together, we also call this bulk material. One of the things that I'm sure you all know is frustrating in chemistry is the fact that there's 5 different names for the same thing, right? Depending on who you talk to, which field, since what we're doing is like chemistry and physics overlapped, the physics people have their words they like to use, the chemistry people have their words they like to use, and then just depending on how we're talking about it. So classical level is at least 10,000 atoms, usually a lot more than that. You know, enough that it's kind of acting like just a chunk of material at some point. We call that bulk material, and that's where you just start treating it like you would in any other class you've had. Now you'll notice there's a funny gap between the quantum level and the bulk material. That's the nanoscale material that's kind of behaving quantum mechanically and kind of behaving classically. There's a lot of interesting research going into that area, that space in between. People try to apply quantum mechanics to this space in between, and you need supercomputers crunching numbers for like a year or 2. You try to do classical mechanics for that range, and you miss properties, you miss behaviors. But this is the correspondence principle. It says, look, this quantum stuff we're doing, as we get to larger and larger materials, it better just behave like the material we've already seen. So that's the one thing that kind of comes out of the fact that quantum mechanics is really a special case of classical mechanics. There's a second thing that makes fun of what I just said. And I called it this. This is not a phrase I've seen before, but it's a really interesting thing that happens a lot. I'll fall into this trap. Every time you hear somebody talking about quantum mechanics, they fall into this trap. Because it kind of relates to classical mechanics, it's built off of the back of classical mechanics, we always try to make a relationship between classical mechanics and quantum mechanics. But at some point, it always fails. Something goes wrong, you miss properties, you miss behaviors, and you can say, oh, it's kind of like this thing you see in the world, but not exactly. So I'll fall into this trap where I make some analogy of like, oh, it's like this thing, but it's not, right? It gives us a good framework. So the classical analogy delusion is essentially we can make comparisons it'll eventually go wrong. While you are all discussing your writing, I heard the term spin come up at least once or twice. And it's one of the only things that we really, quantum numbers and spin is some of the only stuff we know from Gen Chem or before now about quantum mechanics. And spin is one of these perfect examples of a classical analogy delusion. We call it spin because it does a good kind of relationship comparison of the properties we see if we're talking about like a ball that's spinning. But it's not what's actually happening. We see the same thing when we hear the term wave-particle duality. That's another common one that people hear before they take a quantum mechanics class. And this idea that it's duality is also kind of incorrect. It's just a quantum particle. And as we interact with it, we either interact with the wave properties or the particle properties. It's always both. It's not one or the other, and it's some combination of the two that we have no classical analogy for. But we try to make analogy like, oh, it's this or that, but it's not one or the other. It's how we're interacting with it that makes it look one way or the other. And so classical analogy, that's part of where we run into this problem of we try to make relationships because no one's got, coming into this class, no one's got a good sense of what quantum mechanics is. No one has a life experience of what how quantum particles behave. I've been doing this for years, and I don't have an experience of it. I have a theoretical understanding of it. I've never seen a particle behaving quantum mechanically, because I can't observe it. I need computer simulations. I need computers reading outputs. Same thing goes for chemicals, right? You've never seen a molecule sitting by itself. You can't observe that on your own. You can use electron spectroscopy. You can use HPLC to separate them out. You can see peaks that tell you those chemicals are there. You can do your proton NMR, and you can see, oh, there's some methyl group there. You never actually see a methyl group with your own eyes. So we'll try to work on that. But we're going to start with kind of some classical mechanics things. I'm going to try something weird. Let's see if this works, because I need more whiteboards. Middle? Yeah. Okay. So let's do, since this is going to start with some sort of classical ideas, the idea today is that we're going to talk about some classical mechanics, some things that might be familiar from your general physics classes, and then we'll see how those core ideas are going to get used in this quarter. So I'm going to give you a problem to work on together. It's throwing a ball, right? So, right, this is theoretically throwing a ball. I'm not actually going to give you a ball to throw. Okay, so we're going to say, consider a ball. Work in your groups of 4 or 5 again, and I should say, you don't have to mathematically solve this problem. I just want you to conceptually set it up. What are the main steps that you would take to solve this problem? You can work on your own for a little bit, but also I encourage you to work with the people around you. In your discussions, if there was somebody who's like, oh, I'm pretty good at physics, talk to that person. Go for it.
I was trying to do like little mass conversions from 0.12 gram ball. That's ball to ball mass.
Okay, so I think most of you have gotten to the kind of main points that I was hoping you'd get. We start, one of the first things that we do, so the way we solve this problem, in our general physics class, the way we solve this problem is we say, okay, I'm assuming we're starting from the ground, we're not starting from like, part way up because of the body, we're throwing it from like the ground. Awkwardly throwing it from the ground up. We can take the velocity and we can turn the velocity from being the direction the ball is moving, which is in the reference frame of the ball, and we can say, well, let's put it in the reference frame of the ground. And we can say, look, there's an x component and there's a y component to the velocity. So we can take the velocity and we can put it onto what we call an orthogonal basis set. Or we can put it onto an orthogonal coordinate system, right? The coordinate system we are all familiar with is x, y, z. They're all 90 degrees from each other. When we say the words orthogonal basis set, or they're vectors at 90 degrees to each other. The one that we're all familiar with is the XYZ coordinate system. As we get further into this class, we'll find that there's a lot of other coordinate systems we use. R theta phi, R theta z, if we're doing cylindrical coordinate system, spherical coordinate system. And once we get further along, we'll even start using totally new functions to define a new orthogonal coordinate system, which in this class we will often call an orthogonal basis set. That's going to be something particular to our class that we talk about. That's like the x vector, the y vector, the z vector. That would be a basis set for our three-dimensional space. We're going to have a lot of different ways we can talk about that. So the way that we're taught to solve this in classical mechanics is we say, look, there's these velocities, there's some force. The force that we're going to be worrying about for this is going to be gravitational force. So we're going to have mass times gravity is going to be the force that's acting on it. That's our acceleration. And that force is going to be specifically acting against this velocity, right? The force is going to affect one velocity and not the other. And that's the benefit of picking a different coordinate system. Rather than just looking at it in terms of the ball with this one vector, we split it into this different coordinate system that's got two vectors, because then we can impact just one of them. And it's a little bit easier to deal with. It turns out this process of taking one thing and putting it into a different coordinate system, into a different set of equations that describe it, that's going to be something we do in quantum mechanics pretty often. And that's going to be called changing our basis set. Always using orthogonal systems, so that way, because if they're not orthogonal, if they're like at an angle to each other, you have values that overlap. Orthogonal, the values never overlap, they're unique values. So that's one of the important things. We can decompose our velocities into two different things. We also call this process is also referred to, it's related to this idea of separation of variables. So when we originally look at the velocity is traveling in x and y at the same time. Those variables are mixed up with each other. By splitting this up, we're separating out the x variables from the y variables, and we can treat them independently from each other as long as they're in that orthogonal coordinate system. All the x values are completely separate from all the y values now. So we've separated our variables, and we've essentially created two problems to solve: the horizontal problem and the vertical problem. And that's something we do in quantum mechanics pretty often. We take a problem and we're like, hey, doing this with time evolution and spatial evolution is too much. Let's separate our variables so we can just talk about one piece at a time. And if we can, after we separate our spatial variables, we say, okay, let's separate x from y from z, so we have three separate problems to solve rather than one big gnarly problem to solve. So those are all tricks that we're going to be using in quantum mechanics. Now, the thing that's funny about this is we still have just like a definite position. And that's not the situation. Let me make sure I didn't forget anything. We could have used either coordinate system. We could have solved it in terms of just this velocity in x and y. It's just the equations are a little bit messier. So either coordinate system would have worked. Now, the way that we get to doing more quantum mechanical things, let's do this again. I'm going to give you another problem. Now, this problem I definitely don't expect you to solve. This problem I want you to just consider how it's similar or different from this previous problem. So really just focusing on what makes this different. Oh, there it is, okay. So as I'm writing the rest of this problem, just start thinking, what's it look like when you throw a handful of sand? Right, start thinking about it.
Oh, I didn't get that right.
Okay. So I don't want you to actually try and solve this problem. I want you to just conceptualize it, think about it. Think about some time you threw sand or you saw somebody throw sand. How did it move? What would you have to consider in order to talk about this, kind of like problem one, finding how far it's going to travel? Discuss. I think most of you got to the idea pretty quick of like, this is going to be a mess. Don't throw sand. No, this is going to be a mess because it might all leave with the same initial velocity, but because of wind, because of the fact that it's hundreds of thousands of different bits of sand bumping into each other, you're going to end up with this spread of velocities and this spread of positions. It's not going to be just one position. Now keep in mind, we're still doing this with classical mechanics. We haven't done quantum stuff yet, but you can already see how this is starting to, like, oh, we're going to have distributions of things rather than just a specific position. So what happens in this situation is we end up with, like, I'm just making up a shape here real quick. We throw the sand and it kind of like one part stays like a clump, another part clumps up, and like there's bits that kind of move every direction. We throw this clump of sand. And it turns out we can talk about the distribution of the particles after some amount of time. We can talk about the distribution of the particles on the y-axis, and we can talk about the distribution of the particles on the x-axis. So we've got very few particles, we've got a lot of particles less, we've got some particles, and then it tapers off. In this direction, we've got lots of particles, and then just none. So we end up with a distribution right? We end up with a distribution of positions along the y-axis. We end up with a distribution of positions along the x-axis. I can write a mathematical function for this that's some f of y. That's some function of the particles along the y-axis. And I can write some function of this one, some f of x, that's going to give me the function of the distribution of the x particles. I can write this as two different functions. Now, our mathematics get to be a bit of a mess, right? I'm now, instead of taking the derivative with respect to a single velocity or a single position, right, a single position, I now have to take the derivative with respect to a function of them. And I don't even know if these are all going to have the same velocities. That's why I start with this. Now, when we start doing this, where we're doing like a derivative on a function, we give these things special names. This is the time derivative. Let's do this. Let me rewrite that for a second. Right. Essentially what we've got here is we've got the time derivative to figure out the velocity just along the x-axis. We've got the time derivative operating on this function, whatever this, this is like 2 Gaussian functions or something. I don't know. I just made up the shape. Right. In that way, we would call that d by that derivative with respect to time. That would be like a time operator affecting this function. So we're doing an operator acting on a function. And when we start doing quantum mechanics, this starts to be kind of what we have happening in quantum mechanics, where we end up with distributions. And so we've got these operators acting on functions, rather than having a position where we just act on the position. So we end up with some weird things, but this is all done in classical mechanics, right? We haven't done anything quantum mechanical yet. And in both of these problems, particularly for this one, there's a different way we could think about the problem. And it turns out that thinking about force vectors, force is not conserved, right? This is what we call classical mechanics, also called Newtonian mechanics, also called human scale mechanics, right? It's throwing things, balls rolling down hills, all of that sort of stuff. Friction, right? That's all this. It's all done with force vectors, right? That's an object in motion tends to stay in motion unless acted upon by a force, right? It's all in terms of forces. But there's kind of a problem with doing everything in terms of forces. Force is not conserved. Force can be changed, right? And let me do a quick check. 1 through 5 conserved properties. Couple 2s, couple 5s. There's 5 of them. Go ahead and see how many you can say to your neighbors. I'm about to write them down. See how many you can say before I write them down.
Energy.
I think mass and energy are the same.
Mass. Oh yeah.
Mass. Yeah, exactly.
Mass, energy.
So I guess this was, I can only think of one then. The mass and energy.
Actually, that depends on if it's like a collision or not. Charge.
Where's my list of them? There we go.
Overall, anything.
Not money.
Momentum's conserved. I think so. Energy. The 5th one is one that a lot of people don't get. Spin is conserved. Or it's often also listed as just angular momentum.
That makes sense. It's like a Beyblade.
Right, so spin is conserved, angular momentum is conserved. Mass is conserved. This is how we balance chemical reactions. The fact that matter can't be created or destroyed. Charge is how we do our electrochemistry. The fact that electrons can't be created or destroyed, like charge has to go from somewhere to somewhere. This is like redox reactions. Momentum is like a physics thing, kind of that ball being thrown problem. That's momentum being conserved, right? You have to have the idea that you run out of momentum at the top because it's converted to potential energy, right? And it's really energy is conserved. Spin is going to be something that becomes important for understanding spectroscopy. But angular momentum, we're going to look at that one a lot as well. So it turns out that, you notice force is not on here. Velocity is not on here. We could relate velocity to momentum almost because you can relate mass times accelerate or mass times velocity is momentum. But it turns out that there's a different way to formulate classical physics. And they do this in classical physics, and you probably didn't do this in your general class, because it doesn't matter. When you're doing like throwing a ball or rolling a ball down a hill or friction or pulleys, you don't need to do this. But when you're dealing with a distribution of particles that are moving, like throwing a handful of sand, or trying to describe like the diffusion of a cloud, when you're dealing with these large distributions of things, it's more sensible to talk about things in terms of total energy. And it turns out these earlier problems also talk about total energy, because we know that the potential energy, the kinetic energy becomes potential energy, becomes kinetic energy, kind of goes back and forth. But it's this thing we have to kind of slap on top to make sure we're meeting our conservation. There's another way we could do the problem. Again, for the simple throwing a ball problem, it's not that great, but you essentially set up this thing called the Hamiltonian, which is going to be the total energy, your kinetic energy plus your potential energy. Let me actually write that out, since this is the first time we're doing this. I often abbreviate kinetic energy KE plus potential energy kinetic energy is always going to be that 1/2 mv squared term for classical mechanics. It's going to be a little bit different for quantum mechanics. And our potential energy just depends on what problem we're doing. Right? For the problem we just did, our potential energy was gravity. It was that force kind of pushing down on things. So we can talk about our kinetic energy and our potential energy. Framing the problem like this, we can now talk about the total energy of what's going on. And we've got these weird equations. You've done your other P-Chem classes, so maybe this won't look that weird to you. But we essentially have a position vector in x, y, and z, you know, if we're doing 3 dimensions, with respect to time, is equal to the derivative of your Hamiltonian with respect to a momentum vector. So there's going to be a relationship to position and energy, depending on the time and the momentum. So there's this relationship between the things. And the reason this is nice when we start looking at, or actually let's just do this as just an x, y, z point. The reason this is nice when we start doing these large collection of particles is because we can pretty easily transform this to being a derivative with respect to time for some function, some distribution function of x, y, and z. And that can be related to the total energy with respect to momentum in the x, y, z coordinates. Now, this part, we're never going to look at this part again. So if you're like, I don't understand this whole derivative thing you're doing, that's okay. This is just a different way that classical mechanics gets formulated in terms of total energy. And it guarantees that your system is going to be closed. So this ball, like being thrown in the air, you don't have to worry about how does the kinetic energy become potential energy, because you've got the total already in your equations of how you're going to solve this. Again, for that ball being thrown, this is way overkill. It actually just complicates the problem. For this idea of throwing a handful of sand, you kind of have to do it. You kind of have to think about the distribution of energy and operating on that, because all the energy you originally threw, even though we've got this distribution of points and this distribution of velocities, this distribution of momentums, the total energy you originally put into it all has to be taken into account. That's total, right? That total energy you put in, it doesn't get created, it doesn't get destroyed. These bits that are going faster are because these bits are going slow. The total energy is still there. And so when you start doing these large collection of particles, it turns out doing your Hamiltonian for your kinetic energy and your potential, your total energy, just guarantees that you're keeping track of everything at once. So it turns out that it's a little bit nicer that way. The main things here, let me make sure I didn't forget anything. Using the Hamiltonian for total energy, distribution, yep. Okay. Now this is where we start to get into these are the main ideas that we're going to have that we're going to translate into quantum mechanics. It's this idea that we can formulate physics in terms of total energy, a Hamiltonian. It's this idea that we can have a distribution of particles, and this idea that we can take a vector in one direction and we can split it into two separate problems. Question?
What is R?
R is just like a position, right? So if we had an XYZ coordinate system, if we had like a XYZ coordinate system, it tells it's that point right there. Or it just tells one single point, rather than having a function that gives us a distribution of points. Other questions? There are going to be four main problems in physics in the past and chemistry that give rise to us combining all of these classical ideas and being like, we have to do something a little bit different. Right? These all came up and were all solved in the early 1900s. And this is what your first batch of reading is about, 7A in the chat. How many, 1 through 5, you started reading? I'm sorry. The first section of reading is like weird. We'll talk about that. The rest of the time we're going to talk about the reading, and then we should also talk about the syllabus at some point, I guess. So the four main problems are going to be black body radiation. This was kind of the first thing that was solved this was solved by Maxwell Planck, and it was kind of the first thing where people were like, whoa, energy is in specific energy packets. Everything we've done in classical mechanics, even this distribution of particles thing, every particle could have any amount of energy it wanted, right? It could have a lot of energy or a little bit of energy. It's a complete, I think of it as like turning a dial. You could turn the dial to any energy value. Turns out the way that Maxwell Planck was able to solve this issue with black body radiation was he said, well, what if that wasn't true? What if there were specific packets of energy that were possible? Like there's a minimum size to energy. So when you get down to a small enough scale, there's like a minimum chunk of energy that can't be split. Like an atom can't be split. There's a chunk of energy that can't be split. That's a specific quantity of energy. That specific quantity of energy is referred to as a quanta of energy. And when you're on the scale where you're dealing with quantas of energy, you're doing quantum mechanics. So quantity, quanta, quantum all have that same like Latin prefix as like specific amount. Like not any value, specific amount of energy. So black body radiation was the first one. Then Einstein, of course, came along, and he solved two problems that put this on the map. That's the photoelectric effect. And heat capacity. At low temperature. And then the last thing that actually relates to what we're doing, heat capacity kind of relates to chemistry, right? That's a chemical. We can talk about that material property depending on what it's made of. But the one that really relates is atomic emission spectrum. This is going to be our IR, our UV vis, our radio wave, if you're doing rotational spectroscopy, even our NMR, all of that stuff is going to be here. So a lot of how we know what's happening in chemistry is through understanding this atomic emission spectrum part. So that's another way that this is all going to relate. You know, there's understanding the electrons, but all of this is usually energy interacting with the electrons, except for NMR, that's energy interacting with the nucleus. Shielded by the electrons, but same thing. So, what else want to do? I don't want to get into the postulates yet. Next class would be the postulates and kind of getting into the postulates. The postulates of quantum mechanics are kind of like the base theory. There's 5 different things where it's like, hey, if we all agree with these 5 starting things, there's all of this other stuff we can do. So let me talk for a little bit about the reading. I'm actually going to go ahead and